Welcome back class to our course Mechanical Behavior of Materials. So we have already discussed about the strengthening mechanisms, and Professor Sushant Sekhar has also discussed with you about tensile testing. Okay, so today what we are going to do, we are going to talk about other mechanical tests like hardness testing and impact testing, etc. Okay, so we'll start with the hardness testing and then we'll talk about impact testing. So let's talk about hardness testing. Okay, so what is, first of all, what is the hardness testing and why it is being used? We'll discuss about that, but let me begin with saying that in material science community and metallurgical community, people use a lot this hardness testing. It's one of the most versatile techniques when we talk about measurement of mechanical properties, and it is mainly measured on the surface. Okay, so let's talk about in details about hardness testing. So what is hardness? So it's a measure of a material's response or resistance to localized plaster deformation. You already know what is plaster deformation, right? So okay, or say permanent deformation. And basically we do everything on the surface. Okay, so hardness is typically measured on the surface. So it's materials response or the resistance materials is going to give when you try to deform plastically the surface of a given material. Okay, and that is how hardness is measured. So there are three types of hardness we are going to discuss today. First one is stretch hardness. Then we have rebound hardness. And then lastly, indentation hardness, which is one of the famous one. Okay, most famous one among these three, indentation hardness. Okay. So let me give you some introduction about hardness before we talk about all these hardness, three different type of hardness. So introduction, 2 to 3 points about hardness. So the first is that you see, typically hardness is being used frequently by material scientists and metallurgical scientists because of some of the reasons. The first is that it is simple and inexpensive. Not I should not say inexpensive, relatively inexpensive. Okay, so it's relative term. Okay, so if you compare to your tensile testing, what Professor Sashank Shekhar discussed, right? You have to prepare a sample, right? You have to use EDM, etc. Then polish it, then use a tensiometer, etc. So that is cumbersome. Although it is a very good technique, it is a slightly cumbersome. So in that sense, hardness becomes much simpler technique to measure mechanical properties. And second, the equipment what we use for hardness measurement is not that expensive. Okay, so it is a relative term. Relatively, it is slightly inexpensive. So that is point number one. Second, the test is non-destructive. Okay, so now again compare with your tensile test. There you are going to fracture the sample, right? Here in hardness test, we are making indentation, or say we are doing scratch on the surface of the sample. So you are actually not destroying the sample itself. Okay, you are actually giving a localized deformation on the surface of the sample. So this test becomes non-destructive in nature. So you are not actually fracturing or giving excessively deformation to the sample. So this is the second point. And third is, it can give you an indication of the strength. That means, if hardness is high, you can say that, yeah, strength is also going to be high. So it gives you an indication of the strength of the given material, although you cannot directly calculate the value of the strength, but it gives you qualitatively what could be the strength in the relative sense, higher or lower. Okay, so these are the 3 points, why researchers use hardness a lot, okay, to measure mechanical property, that to hardness. Okay, again remember, it's a surface property rather than the bulk property. Tensile test is your bulk measurement. So now let's talk about the history, how it has progressed over time. So historical perspective. Okay, so the first hardness measurement, let me change the color one second here. So it started in 1722 here. Okay, so where it is related to the scratching the surfaces. Okay, and then in 1822 the development of Mohs scale happened. Okay, and we are going to talk about this Mohs scale in couple of minutes. Okay, so there you will see that there is a table of a 10-point scratch hardness table, and depending upon the scratching ability, you can guess what kind of mineral is present. Okay. Now after that, John Brinell developed Brinell hardness in 1900. Okay, and then rebound hardness is around 1907. Then Rockwell hardness came into picture at around 1920. Okay, where we are going to talk about preload method. So this Brinell, Rockwell, Vickers, and Knoop, all these are indentation hardness. Okay, Mohs scale is related to scratch hardness, and in 1917 you have this rebound hardness. Okay, and then around 1925 Vickers hardness testing method was developed. Okay, and it became very famous. Now we are talking about instrumented hardness like nano indentation. Even in Vickers micro hardness, you can measure using IIT instrumentation indentation technique. Okay, but we will focus on mostly scratch in the hardness. and then Rebound hardness, then Brinell, Rockwell, and Vickers hardness. Okay, so this is how I'm going to talk about the progress of the topic. Okay, so let's start with the scratch hardness. Okay, so the name itself suggests, right? Scratching. Says scratch hardness. So you are somehow scratching the material, and based on that, you're trying to understand what could be the hardness of a given material. Okay, so here it's a Mohs scale. Okay, and this is typically for mineral. So this is the table here. So we have Mohs hardness varying from 1 to 10 in increasing order like this. Okay, and different minerals have been listed here. So one corresponds to say talc, then 4 corresponds to fluorite, and then 10 corresponds to diamond. And we know diamond is the hardest one, right? So 10 belongs to the diamond, and the softest in this list is talc, and I have also given you the chemical formula. Okay, so it shows, this table shows what it shows: scratch hardness of various materials or minerals. Okay, so it also tells you the ability of a harder material, a mineral, to scratch a softer mineral. Okay, so what does it mean? Suppose I take fluoride and try to scratch talc, right? So fluoride can scratch talc very easily. Okay, and if I can see it, I know that fluoride is harder than talc. Okay, and if I do the opposite, if I take talc and then scratch fluoride, it is not going to scratch fluoride. So we know that talc is softer than fluoride, and that is what I wrote here, right? This table nicely tells you the which one is harder mineral and which one is the softer material. So it gives you a scratch hardness of various material. That is point number 1. Now second, it is this table can give you it is a convenient way to help identify minerals. Okay, so suppose you are going for a field trip, okay, and you found some minerals and you want to know, which mineral is that. You want to guess it. Okay, so you can use this table to slightly guess, which type of mineral it can be. Okay, so it is a convenient way to help identify minerals. Okay, so suppose again you went to a field trip, and then what is the scratch hardness of your fingernail? It's around 2.5. So if you use your fingernail, it will be nearly say around 2.5. Okay, and if you take say steel nail, it will be around 6.5. Okay, so you are going to a field trip and you found some mineral, and if you are able to scratch the mineral using your fingernail, you know that the hardness, scratch hardness or Mohs hardness of that particular mineral is lower than 2.5. Okay, so and similarly, if you are able to scratch a particular mineral, say using steel nail but not using fingernail, you should be able to know that the Mohs hardness lies between 2.5 to 6.5. Okay, so basically you can use some common objects for which you know the hardness. Okay, and then you can figure out what could be the Mohs hardness of a unknown mineral. Okay, so this is very important for mineralogists. Okay, they use this type of hardness a lot. So this is one type of hardness, which is Mohs hardness, okay, or stretch hardness. Now we'll talk about rebound hardness. Okay. Now again, the name itself suggests rebound hardness. So what we are going to do, we are going to use the concept of rebounding. Okay, so it's like, you know, you are having a, say, ball, right? Tennis ball, and then you throw on the wall and then rebounds, right? So it is going to come back, and then you can measure how much distance it has covered while coming back. Okay, so that's the same concept we are going to use when we talk about rebound hardness. So if you see here, I have a schematic. So this is how you measure the rebound hardness. You have a hammer, which is typically of, say, diamond rounded tip. Okay, and it's a glass tube here. Okay, and then you have a scale here. So this hammer is going to be released, something like this. So this is situation number 2. Okay, and it is going to hit the sample. So your sample is at the bottom here. Okay, so your hammer comes down, it hits the sample and then rebounds back. Okay, so it travels this much height. Okay, now you have to measure what is the rebound hardness, and there are machines, you don't need to do anything. This is the concept, how it works, what is the principle of measurement of rebound hardness. Okay, so it measures the rebound height, okay, based on the scale, and then it gives you a value. Okay, and that value will be called as rebound hardness. Okay, so the higher the rebound hardness, higher is going to be the hardness of your given material. Okay. So the harder the material, the higher the rebound. Okay, suppose I have two material A, and then another one is B. So two material, okay, and I am doing rebound test. So in one of them, after rebound, my hammer was here. So this is my rebound height for, say, A, and then in another one, this is the rebound height for B, HB. Okay, so here HB is greater than HA. This means capital HB is greater than capital A, where this capital H is your hardness or rebound hardness. Okay, and the small h is your rebound height. Okay, so this is how we measure the rebound hardness. So higher the rebound height, higher is your hardness of your material or alloy. Okay, so the one of the advantage of this type of hardness is that the machine what you use is portable and it is very easy to handle. So that is one of the advantages. So it's portable and easy to handle. Okay, so this was about rebound hardness. So we have covered scratch hardness, that is the Mohs scale, and then the rebound hardness. So now we'll come to the third one, the most famous one. As a material scientist or metallurgical engineers, we use indentation hardness. Okay, and you might have heard already about Brinell testing and Vickers testing and Rockwell testing. So we'll talk about them one by one. Okay, so what is the central concept when we talk about indentation hardness? So let us understand it. So again, say we have two alloy. This is A and the second one is B. Okay, so two material. And say my indenter is of ball type and we are indenting both of them. And I am applying a load of P, constant load on both of them. Okay, so we have two different alloys and then we are using ball indenter. Okay, so this is your indenter here. Ball indenter. So see, indentation hardness means you have to indent it. It's like, you know, you have this nail and you're trying to pierce it, right? So you're making an indent on the surface. So we have different type of standards for that, like Brinell hardness, Vickers hardness, and Rockwell hardness. Okay, so basically you have to indent the surface. Okay, so you are applying a load P, so it is going to go to some depth. Okay, so suppose in alloy A it went up to a depth of say T1. And in alloy B, it went up to a depth of T2. Okay. So now we know that T2 is greater than T1. Okay. So by logic, one can always say that B is softer than A, right? Because it has gone to a higher depth when we are indenting the surface. Okay. So if it has gone to the higher depth, B is going to be softer. Right? So indentation, what we do, we see the top view of it. So if I try to see the top view of say alloy A, I'm going to see a circle. And if I try to see the top view of alloy B after indentation, I am also going to see the circle, but it will be of larger diameter. Okay. So if this diameter here is D1 and it is here D2, so we can write D2 greater than D1. Okay. So again, remember it's a ball indenter. So when you are trying to indent it, you are going to get that. If you see the top view, you are going to see a circle. Okay. And since T2 is greater than T1, you are going to see a larger circle in alloy B. Okay. So if we have T2 greater than T1, so D2 greater than D1, where D is your diameter of indent impression. So this is your indent impression, both of that, these two, right? And T is your the depth of indentation or indentation depth. Okay. So finally, you can write H1 greater than H2. Okay. So this is a central concept of indentation hardness, that we try to see the impression, right? What is the impression of the indent you have made? Okay, but in Rockwell, we don't see the impression. We measure the depth of the indentation. So in Rockwell, we will use the concept of say T2 greater than T1, and in other Brinell and Vickers, we see the indent impression and then measure the diagonal length or say diameter of the circle circle, which is the indent impression, and then finally we measure the hardness. Okay, so this is the central concept of indentation hardness. So in general, the hardness we can write as load by indentation area. Okay, and this is what we are going to use when we talk about Brinell and Vickers hardness. So there are three types of indentation hardness, which we are going to discuss in the class. So the first one is Brinell hardness. Second is Vickers. And the last one is Rockwell. Okay, so we are going to discuss these three, Brinell, Vickers, and Rockwell. So let's start with Brinell first. Brinell hardness testing. Okay, so here we typically use 10 millimeter diameter steel ball. Okay, so your indenter in this case in the Brinell testing is steel ball of 10 millimeter diameter. Okay, and typically the load what we apply is 3000 kgf. Okay, kilogram force. Kgf is kilogram force. Okay, but for softer material the load can be reduced. Okay, but this is the standard 10 millimeter diameter steel balls and 3000 kgf. Okay, in some of the cases if your material is hard you can also use tungsten carbide. Okay, so tungsten carbide you can also use for hardened material. And this is the setup. So this is the Brinell hardness tester we have in our lab here at IIT Kanpur. Okay, so we show this test to all UG students in our department. So you place your sample here. Okay, so you have anvil. Okay, and then indenter is here on the top. So here. Okay, so you can see this is your indenter. So you place your sample. Okay, and then you make an indentation, then take out the sample, go to microscope and see the indent impression as I discussed just before. Okay, so this hardness measurement in this case can be given as a BHN, which is Brinell hardness number, and it will be given as 2p divided by pi d minus square root d square minus small d square. Okay, where P is your load and it is in kgf. D is your indenter diameter. So here ball diameter, which is typically we use 10 millimeter. Okay, and then small d is your diameter of indent impression. Okay, so since we are using ball indenter of 10 millimeter, right? So suppose I have alloy or material and we are using ball indenter here, right? something like this. Okay, so this is your ball indenter, and this is your sample. So a ball indenter is placed on this place here, right? See the diagram I'm marking here. Okay, so now if this is the side view, and if you see the top view of it, you can see the indent impression. Now if I see the top view, and it is going to be something like this. Okay, it's going to make a circle. Okay, so what we do, we measure D1, and then along the other direction, perpendicular direction, we measure D2. Okay, so we measure two diameters, D1 and D2. So here D1, D2 are diameters. Okay, so diameter of the indent impression when you see from the top, and you take the average. So this will be average of D1, D2. So this D, if you remember, is here, right? So this will be D1 plus D2 by 2. Okay, so you know P because you are doing the test. You know the ball diameter that is also given to you. So what you have to do, you have to use this indenter, then take out the sample after indentation is done, and then go to microscope, see the top view. You are going to see a circle. Okay, and then measure the dimension, diagonal diameter along two perpendicular directions. Those will be D1, D2. Take the average of those two, and that will be D, small d. And then you can use this formula, BHN equal to 2p by pi d, and d minus under square root of d square minus d square, and then you can figure out what is the hardness in Brinell scale, okay, which will be given in BHN. So here I am showing you one example, which is for mild steel. Okay, so load is 200 kgf. Okay, so 250 kgf. Sorry. Okay, so what you have to do, as I just mentioned, you have to measure two dimensions. So you can measure, say, D1 along this direction, and then D2 along this direction. And if you do that, roughly D1 will come out to be 1089 micron meter. D2 will come out to be 1080. These are rough numbers, okay? Micron meter. Okay, so D average you can calculate. That you can calculate. You know what is P that is given to you, that is 250 kgf. So you can calculate the BHN number. Okay, from this formula. Again, this D and small d will be in millimeter. Let me write. So both will be in millimeter, and P will be in kgf. Okay, so this is how you calculate the Brinell hardness number. Okay, so especially when you use steel ball, the Brinell hardness number is not going to be accurate when your material is very, very hard, right? Because see, you are using a steel ball, there is a chance that your steel ball is itself deforming. Okay, so if you are at your material is hard, it is better to use Vickers, which I'm going to talk about. There we use diamond indenter. Okay, and diamond itself is very, very hard. Okay, so your Brinell hardness is not reliable at very high hardness values. So that means a harder material. Okay, that is point number one. In all the hardness tests, whether it is Brinell, Vickers, or Rockwell, your surface has to be smooth and you have to polish. Okay, so basically when you want to do any hardness test, you first polish your sample using conventional metallography technique, and then use either of these three indentation methods depending upon your material, and then you can calculate what is the hardness value. Okay. Second, it is not very suitable for thin samples because of larger indenter impression. Okay. So the first disadvantage is that not reliable at high hardness value. Okay, say greater than 400 or so. Okay. And the reason is because your steel ball itself will start deforming. Okay. That is point number one. And second point is not very suitable for thin samples, thin film, etc., or where your sample thickness is not that high due to larger indenter impression. Okay, so this is what Brinell hardness is all about. So now let's talk about Vickers hardness measurement. So here, what we are going to do, we will use the indenter is going to be diamond pyramidal. Okay, so this is going to be your indenter. So we are using diamond instead of steel ball when we talk about Vickers hardness test. Okay, and this is the indenter shape. So this is your indenter here, Vickers indenter. Okay, and if you see this, so first of all, you can see here, right? Your base is square shape. Okay, and if you take this particular surface and this particular surface, the angle between these two is fixed, and that is 136 degree. Okay, so the angle in the diamond pyramidal indenter used in Vickers test, the angle between the two opposite face is going to be 136 degree. Okay, again the indenter is made up of diamond, and if you indent it, your indenter shape, indent impression shape is going to be something like this. Okay, at the bottom. So what you do here, suppose you have material and you are indenting it using your diamond pyramidal indenter, and if you see the cross section now, it is going to be something like this. Okay, so this is your side view and this is your top view. So finally you are going to get an indent impression which will be this from top view. Okay, so you polish the sample and then go to your indenter. I will show you the image of the indenter a machine we use here in our lab. Okay, and then indent it, and then you measure what is this two diagonal length, D1 and D2. Okay, and then you can take average, that will be D1 plus D2 by 2. Okay, so there in the Brinell hardness testing, we were measuring diameter of the indent impression. Here we are measuring the diagonal length of the indent impression. So you measure D1 and D2. Okay, so I have machine setup. Okay. Okay. So anyway, so machine setup is it looks similar. Okay. Only thing is your diamond indenter is different. Second, you are going to have a microscope attached to it. So now there are different microscope. Why? Because you want to see the sample surface before you make an indentation. Okay. So you take the sample, place on the anvil, then use the microscope attached to the machine, then see the surface where you want to indent, then bring the indenter on the surface and start your test. Okay, and then remove the indenter. Now there are two ways you can measure this D1 and D2. You can use the same indenter, same microscope attached to the machine, and then there you can measure D1 and D2. Or you nowadays, we have sophisticated machines and attached equipment, so there are cameras attached to your machine, and then camera can capture your image, and then you have a computer attached to it where you can nicely measure what is your D1 and D2, and finally you can find out the average, which will be your final diagonal length when you calculate the hardness. Okay, and the hardness can be given in the Vickers hardness test is, so we use HV when we call Vickers hardness. Okay, and it will be given again, the formula remains same, P versus area. Okay, so here area is your pyramidal indentation area, right? So that will be given as 1.854 P by D square. So this is for your Vickers indentation, where P is your load, again in kgf, kilogram force, and D is your average diagonal length. This is in millimeter. Okay, so this is how we measure Vickers hardness test. I have an example here. So this is for aluminum. It's for aluminum alloy, say 7075, and then we are using 500 GF load. So your load is given, P is given as 500 GF. And this is the indent impression I was talking about before, right? So what you have to do, you have to measure two diagonal here. So one is going to be this one. Okay, and another is going to be these two. So you have to measure D1 and D2, and then find out what is the average of D1 and D2. Okay, so here if you try to solve, it is going to be, D1 is going to be nearly say 75 micron meter, and D2 is going to be nearly about 74 micron meter. So you can calculate what is going to be D. Okay, you know what is P, you can calculate what is your HV. Okay, and if you do that, it will come out to be, in this particular case, the hardness will be 167 nearly. Okay, so this is how we use Vickers hardness test to measure the hardness of a given material. Okay, so what is the advantage? So one of the advantages I already told, right? That when you use Brinell, you cannot go for very hard material because your steel ball can itself deform. Okay, so if you have harder material, it's better to go for Vickers diamond indenter. Okay, so that is the advantage when we use Vickers hardness test as compared to the Brinell hardness test. Okay, so now last one is your Rockwell testing. Okay. So now we'll discuss about Rockwell testing. So this is the setup we have in our lab here. Okay. So you place again your sample, then you have indenter on the top, and then you make an indent on the sample. Okay, so here instead of using microscope etc to see the indent impression, right, it automatically gives you the value of the Rockwell hardness. Okay, so here if you see the scale on the top in this particular image, okay, that I have magnified, and you can see scale C here and B here. We'll discuss what is B and C, but most famous, right, B and C scales in Rockwell hardness. Okay, so you can use this scale, and this dial will give you the value of your hardness, okay, of the material you are testing. So instead of measuring the D1, D2, diagonal of the diagonal length or the diameter of your indent impression in Brinell test, what we did here, it will automatically give you the hardness value in the dial. Okay, so the indenter here we are going to use either we can use ball, or we can use cono spherical, or say diamond cone we also say. So that is something like this. Okay, and this angle, this particular angle is 120 degrees. Okay, so this is diamond cone. Okay, so how do we do this test now? So basically we apply first of all something called minor load, as I have shown here. Okay, so this is the schematic how your indenter is moving on the sample, and this is another schematic corresponding to the top image. Okay, and let me explain this. So what we do, we first apply a minor load on the sample. Okay, one of the advantage is that if you have some rough surface etc, you are going to get rid of that effect. So you apply minor load of F0, and that corresponds to this particular point here. So this is your sample surface, this line. Okay, so you are applying a minor load, so you attain some depth. Okay, this particular depth here. Now what you do, you now apply major load onto the minor load. So you have minor load of F0 and then major load of F1 and total load of F, okay, which is equal to F0 plus F. So you are going to reach to some distance here. So this corresponds to a depth at a load of F, which is equal to F0 plus F1. Okay, so this is my total depth here at this particular point from the surface. Okay, now what you do, you remove the additional test force of F1. So you are removing the major load. So you are removing here. So your indentation direction is shown by dotted arrow. Okay, so this is how your indentation direction is going to be with respect to time. Okay, so after you remove the additional test force F1, your depth position is going to be this one, C. So here you have C, and here also you have C. Okay, so you all now you have only minor load of F0 applied on your sample. So what you do, you measure this distance E, and this you use to measure the hardness of your material in Rockwell scale. Okay, so if we use cone indenter, the Rockwell hardness will be given as 100 minus E divided by 0.002. Okay, and if we are using ball indenter, so Rockwell hardness will be 130 minus E by 0.002. Okay, so depending upon whether your indenter is diamond cone or ball, right, you are going to use two different formula like this. So, and that will be depending upon this value of E. Okay, and again the Rockwell indenter gives you automatically the values. Okay, so here I am showing you a table. So this is for regular Rockwell. Okay, so this is your Rockwell scale overall. And this is for superficial. Okay, so there are two types of Rockwell scale. One is regular Rockwell scale, another one is superficial Rockwell scale. So in regular Rockwell scale, you are going to see your load value is high. Okay, so here I have mentioned in this column the type of indenter, and this is the scale. And as I mentioned before, B and C are the most famous one. So when we use B scale, if you remember the dial I showed you before, right? So there we had B scale and C scale. So if you use B scale, the indenter is going to be 1/16" steel ball. Okay, and if you see scale, it is going to be diamond cone with 120-degree angle. Okay, and in all the cases, you are going to have a minor load which is F0 of 10 kgf here, right? This F0 value. Okay, then we also applied major load onto the minor load. That will vary depending upon the scale, right? So for A scale, it is 50, for B 90, and C 140. And then total load is the summation of minor load and major load, which is given like this. Okay, so you have different scales in the regular Rockwell measurement. Okay, so depending upon the material, you would like to go for different scales, but again, the most famous are B and C. Okay, now superficial came into picture, especially when you want to do the hardness testing of, say, electroplated materials, thin film, etc. So here the requirement is that you don't want to go to very high depth, right? So you need to reduce the load. So if you see here in the regular one, it was of very high load starting from 60 kgf, goes up to 150 kgf. Here in superficial, it starts at 15 and stops at 45 kgf. Okay, and the scale name is given as a 15 and 30 and 40 and that indenter will be diamond cone. And then when we have T, then it will be steel ball. Okay, and minor load is also reduced. Total load is reduced, so minor load is also reduced from 10 to 3 when we have superficial scale. Okay, so I have listed only some of them. You have many more in scale of, say, W, S, and Y when we talk about superficial Rockwell scale. Okay, so this is what I wanted to discuss about hardness testing, especially the indentation on Rockwell, Vickers, and Brinell. So let me summarize the three scales. So we have test. I'm going to list test here. Then what is the indenter? This will help you in, since I am going to make a table, this will help you in understanding or, capturing what type of indenter you use in which type of test. Then here we are going to have shape of indentation, side view, top view. Okay, So the first is your Brinell. And what do we use indenter in Brinell? Either steel ball or tungsten carbide ball, right? And both are say 10 millimeter. 10 millimeter steel or tungsten carbide ball. And if you see the side view of it, it is going to be spherical, right? It's a ball, so it is going to be spherical. And if you see the top view, it is going to be circle. And we'll measure D1 and D2. So average is D, and here your ball diameter is your capital D. Okay. So this is one. Second is your Vickers. Here we are using diamond, pyramid. Okay, and that was 136-degree angle, if you remember. So this particular angle here is 136 degrees. So this is your side view. Okay, so the opposite face, the angle between the two opposite faces is going to be 136 degrees. Okay? And if you see the top view, going to be square, and then you have to measure D1 and D2. So D is going to be D1 plus D2 by 2. Now the last is your Rockwell. So here we will use diamond cone, 120-degree angle. Okay, if you remember, or we can also use steel balls. And the size of the steel balls or spheres are 1/16, 1/8, 1/4, 1/2 inches. Okay, and if you use diamond cone, it will be, so this is the side view, right? And this angle was 120, right? And if you see the top view, it's a diamond cone, so it is going to form a circle. And now if we have a steel sphere, it is also going to form a circle. Okay, here we have two scales, Rockwell, superficial and regular, right? So 60 kg, then 100, then 150. This was regular. And then we had 15, 30, 45. This was superficial. Okay. So we have discussed about Rockwell, Vickers, Brinell hardness test, that is your indentation hardness. We have also discussed about scratch hardness and rebound hardness. Okay. Thank you.